Good day, everyone. I'm at the beginning of this video. I need to give my apology for being absent for a long time, but I was really busy in my studies and some stuff. Today, I will continue explaining how to make input in Caesar, and in this series of videos, I will start to explain how to evaluate the nozzles, the equipment nozzles against the loads that coming from the pipe. And I will start this with the API 650 for the well storage tank. And I will show you today how to make the calculation for the radial expansion of the shell and the bulging of the nozzle, which is the rotation of the nozzle, and how to calculate the allowable based on the API 650 based on the Annex B. Let's start. First of all, let me explain some stuff. W, which is mean the radial expansion of the shell. Theta will be the rotation due to the bulging of the body of the shell. And we have the pressure and the settlement. The settlement is the foundation of the tank after filling the tank with hydro test or due to operation. It will have to be settled. The foundation will settle down, which means it will go downward with a certain amount of millimeters, maybe centimeters, and this is calculated by the civil group, and it is given to us to consider while we are doing our calculation. Okay. Okay. Annex B is applied to tanks larger than 36 meter in diameter, and only it will be applied if the purchaser is accepted. Okay. Other than that, the purchaser should give you the allowable loads for the nozzles and the radial and the rotation of the nozzle. Let's start our example and explanation here. I will use in my explanation the example which is given here in page P13. In this example, I already did it by my hand, and I will use it, and I will show you my results to explain exactly how to do this calculation, because sometimes it have some errors or you need some more explanation. Okay, let's start this by first of all, we have a tank 80 meters tank with a shell thickness 34 millimeters, and we have a bottom nozzle with diameter 610 and length from the bottle 630 millimeters. Our operating temperature will be 90. Our ambient temperature will be 20. That means that the delta T is 70. The fluid that we are using, the specific gravity of the fluid that we are using is 1, which is mean it's water. First of all, we will take the diameter and calculate the radius, which is 40 meters, and take the radius of the nozzle, which is 305, which will be A. In the beginning of our solution, we need to have the elasticity modulus and the expansion modulus, and this you can get it if you have the material. You can get it from the material tables in section 2 or in the ASME P31.3, or you can use this one here. In our example, we use this table B1A, since we are using the SI units. We have 90 60 degrees working, which is 70 degrees. If we make an interpolation, we will find that our elasticity modulus will be 980 900 sorry 198,000 megapascal, and our thermal expansion coefficient would be 12 times 10 to the power negative 6. Okay. First of all, we will calculate the beta. Beta is a parameter that we calculated from the radius and the thickness of the shell. If we can go here, we can find it. How they explain it's the characteristic parameters, as I told you. Then we calculate the p times the height times the height of the nozzle. Then we calculate the thermal expansion due to the temperature, and it will be alpha times to the radius times to the delta t. This is, by the way, the delta t. After calculating this, we will go to the thermal to the equation that is mentioned here for the thermal growth of the shell, and we will apply it. It's the G times to the H, which is the height of the tank. You can use this one to explain this. You'll find a figure that's showing this. But H is the height of the tank, radius of the tank, elasticity modulus time to the thickness, and 1 minus the exponential of the beta times L cosine beta length. And we calculated, and it will give us 39.65. After that, we will calculate the theta. By the way, I'm not working with the same sequence of the calculation because this sequence is more logic to me. We will calculate the theta, which is nearly the same as the of the thermal growth, the W, and we will find. By the way, this is a point. This is a note you should take it in consideration while you are calculating this equation. Your calculator should be on radians, since the theta is coming with radians. Then you can transfer it to degree. After that, we start to calculate the stiffnesses of the nozzle, and this will be by calculating the parameters of this to go to the chart, which is the radius time divided by the thickness, the radius of the nozzle divided to the radius of the shell of the tank, and length of the tank, length of the height of the nozzle divided by 2 times the radius of the nozzle. What we will do, we will take this data to get the stiffness. How we can get it? We will take L divided to 2A and go to this chart in B2, and we will start to check the L over 2A. Our L over 2A is here is 1, so we will use this chart. And we use the R over T. This is the R over T here. So we will take the R over T, which is 1176.5, which is, I think it's nearly to be here, and go up to 0.0076, which is considered 0.8. So we need to put something like a line here, and we will get to this here. Take care from a point. This chart is coming from downward to upward, which is mean all this is times 2. All of these numbers is 1, 2, 3, 4, 5, 6, 7, 8, and 9 is times 2 negative 6. This times 2 negative 5. This times 2 negative 4. So which means that when we go upward to the 8, which is imaginary to be here, and we go straight here, we'll find that we are 3 times 10 to the negative 4. Let's see, it's exactly 3.1 times 10 to the negative 4. Same will be here. Same will go to get the stiffness on the longitudinal R. I didn't explain this. Here we have on the nozzle 3 main loads, and actually in any equipment we have these 3 main loads. The radial load, which is normally is the axial force on the nozzle, and the longitudinal moment, which is always will be on the moment acting on the body of the equipment, and the circumferential moment, which always will be the moment that coming circular around the body of the equipment. So now we need to calculate it. We will always calculate it, the radial force, which is in the tank here is the radial, but usually it would be the axial of the nozzle, and the longitudinal and the circumferential. In this table number 2a, we get the radial load, which is equal to the K radial stiffness, and the stiffness in the radial, and the elasticity modulus times 2 times the radius of the nozzle. Here we will get the longitudinal in the same way that I've explained to you before, and here we will get the circumferential. When we get this 3 numbers, we can substitute it in these 3 equations, and we can get the stiffnesses for the radial and the longitudinal and the circumferential. After that, we will continue to calculate the allowables of in this part. We are calculating the allowables of the nozzle, and this can be happen by this is the case as the stiffness, as I told you. Here the sequence is different. He starts to calculate the thermal growth and the theta after, but I prefer to do it in the beginning since I have all the givens to calculate them. After that, we will start to calculate the flexibility factors or the flexibility parameters, and this will be x will be xa, xb, and xc. Xa is the length times the radius. Here xp is length of the height of the nozzle minus the radius, and xc is the height of the nozzle. To start drawing the nomograms that he's mentioning here, which is this one, and we are using this as to show the limitations of our nozzle. Our allowables should be inside this, should be located somewhere here inside this rectangle. So after that, we will start to calculate the non-dimensional parameter, which is xa divided by radius times the thickness under the root, which is the square root. The same here, and we will calculate lambda. The sine lambda. Sine lambda is a non-dimensional parameter. It doesn't mention any name for it. Okay. After calculating this 9-dimensional, what we will do, we will go back here to these 2 charts, or 2 graphs, which P4A and P4P, to calculate YF and YL and YC, which is the flexibility factors, our flexibility coefficients. How can we calculate them? How can we get them? We take lambda, the one that we already calculated before, this one, and go located, which was 0.26 here, 0.26, it will be something in the middle here, and take a straight line, vertical line, until it hit the first curve, and go to this direction, and you can get the YF. I think it would be 1.6, 1.7, and do the same until it hit the curve YL, and you can get the YL. Also the same here, you go here and go upward, up until you hit the YC, and then you get the YF and YL and YC. Of course, there's a great variation since we are reading from the graph, but you can make it more accurate. YF based on the calculation of the API is 1.9, 7.2, and 13.4. After that, we take this and substitute in the equation of the nomogram, and we get 0.79, 0.4, and 0.59. Also, we calculate the pressure force on inside the tank. The pressure force is the pressure inside the tank times the pi times the radius of the nozzle square, which we get to OGH times pi times 8 square. Take care that we are using Newton, so you need to divide it using grams per meter cube, and 9.8 will be 9,800, and here we are using meters, not millimeters, so it's 19.2, the height of the tank minus the height of the nozzles, so it would be 19.2 minus 0.630 times pi times the radius square, and here you can get the pressure force. After that, you will draw something like this. It's a graph. You can pick your graph paper and start to locate the lines here. It's 45 lines, by the way. So what you will do here, see this? This is the equation that we calculated here, this space. So you need just what you will do that first we have here, this is the A and here is the P. So 1 minus 0.75 XP RT square root, the square root of the RT is 0.79, so it will be, you will take it here, and this is the starting point for this line, which you will take it 45 degree. The same case here, you will take, you will calculate this, which is 0.4, and 0.4, the point where you will start this line will cross through it 45 degree. After that, you can complete this other two lines coming from the top of the graph 1 to 1 and 1. Okay. Same, you can do it for the circumferential. You will calculate, which is 0.59, and you will do this graph. After that, we need to know the allowables of forces that can we go through it, the maximum allowable force. What we will do, we will take this equations, which is based on the force that you need to get it from the force and the moments that you need to get it from the piping calculation. So we will use all the available numbers, and we keep it the unknown of the FB or the, here by the way it's the FB not P, and the moment L and the moment C. there is a point here I need to point to it, that in the ML we use 0.4 since we are to get it more conservative, so we are here in the middle, which is the more less and the more conservative is 0.4, not 0.79, because this is out of our limits. The inside is our limit, so we are comparing. It should be less than 0.4. Here the radial force should be less than 0.4. The longitudinal moment should be less than 0.4, and the MC moment should be less than 0.59. By the way, we calculate this. I missed here. You need to put MC, ML, and FP. If you check it here, you will find it like this. But I missed it. Sorry, I missed it while I'm writing it. After that, the maximum of the radial force will be 0.4 divided by this number, and the maximum of the longitudinal moment will be 0.4 divided this number, and the maximum of the circumferential moment is 0.59 divided this number, and you will get, this is our allowables for the nozzle, and this is the way that you need to calculate it on the API 650. Let's go to the Caesar and apply this. We have here, and this will be the example that we are working on through this series, that we have here a tank, and this is the example that we have, and two pumps, connecting two pumps, and from the pump we'll go to storage vessel and pressure vessel. I will explain why we are using this. Okay, and this is a simple system, which is not a real system. Okay, and now we go to here. As you can see, I already did this example, but let us delete it and repeat it again. You can either continue this by inserting a nozzle before and mention it as something like this, and put a flange. You can continue this like that, or I prefer, which is not an obligatory and it's nothing, to use a C node with anchor. After we go to the end of the calculation, then the end of the calculation, and then start your calculation. Need to here to put 10,000, 100,000. Here, and insert a flange. Okay. Here our force. We have here 12.5. Okay, cohesion allowance. Piping density, we are using a 106 grade B, 90 and 120. We can adjust this. It's better to be adjusted from here. temperature 150. Let's see. There's a lot of mistakes can be happen if we didn't adjust it from here. So please always try to use the this list in adjusting the in temperatures and pressures. Okay. After that, let's consider a projection for the nozzle. Okay, in this projection, we need to make to calculate the flexibility, which is already we did it by calculating the stiffness here, and we will select to use the API650. Here he mentioned if you need to make a C node for an options. This is the axis of the tank, so we need it to be a vertical, so we put one here. This is the diameter, the thickness, distance from the base of the tank, which was 630. Reinforcing shell diameter, we have 80, thickness 34, elasticity modulus was a coefficient of thermal 12 exponential, how much was? Temperature change was 70, and the height of the fluid height in millimeters. And here, if you need to put the displacement, you can use it, but since we will use the rotational and the other displacement, it's better to put it none, and we will use this displacement. I will do this like that. Put 30 here. Okay, after we applied the stiffness and the data of the stiffness, we need to insert the displacement. How we insert the displacement as it had been calculated. We put the radial growth in the x direction. So we put 59.65. Also, we need to have, if we have any growth in the tank 630, we can put it as 0.9 if we calculate, if we do the same calculation again, but instead of using the radius of the tank, we can use the L, which is 630. We will get 0.53, and we will insert the rotation. The rotation will be in the tanks, since our calculation here is like that, so the tank will rotate, or the nozzle will bulging, the theta will be rotating on the z direction, so we need to put the rotation on the z direction. So theta, take care, this theta is radian, we are using degree, so we need to put this one, which is 1.85. Okay. The second displacement that we are using, by the way, we will use three displacements. D1, which is the operation for the 90 degree, D2, which is the design for the 120, and D3 is for the tank settlement displacement. So we need to know the thermal growth for temperature 120. Let me show you one trick here that can be using instead of redoing the calculation again. If you run the check here, you'll find that the Caesar already done the same calculation that we already did. And here, you'll, in the radial deflection, it will give you the W, which is 59.61, and the longitudinal rotation, which is minus 1.85. Okay, let the Caesar redoing the calculation for you. By the way, we need to put this negative. Okay. Let him do the same calculation by changing the temperature here from 70 to 120 and redone the calculation. And you will have the thermal gross calculated for you here, which is 83.61. The same rotation, there's no difference in rotation, but it will be on the W, the thermal growth. So 86.61, 83.61. So we go here and put 83.61, and we can do the same in which will be 0.756. By the way, we made a mistake. We can go back and we figure out this mistake. We don't use 120 because it's already minus the ambient temperature, so we need it to 100 only. So run it again, and you will get 74.01. Displacement is 74.01, and rotation is the same, 1.85. Okay, here, as I mentioned, we will put a settlement minus 20 millimeter settlement, and we need to go back here and change the temperature back to 70. Sorry. Okay. Now I already entered the data for the tank. We need to run check. I don't have any problems. Now we go to the load case. In the log case, if we load the default load case, you will find he will give you one extra operation, sustained operation, which is no need, or operational load case. You don't need it because he has a displacement D3. This is why he will put this operation, so you need to just to delete it, and you need to take the D3 and add it to the design operating case and the operating case. This is why, because you consider the thermal growth and all the displacement that you need plus the settlement. It will be only added in the operational case. Then you run the analysis. After we run, we need now to set the limits that we already calculated. So what we will do, we'll go back to the input file. To set our limits or the nozzle limits. How can that be done? First of all, we need to go to the last node. Then we put the nozzle limit check for absolute, and we need the vector of the tank, which is y, and we'll insert here. Before I start this, let me explain something. There's something called a local coordinates. The coordinates that we are using here is the global coordinates, that we call it the global coordinates. So when we need to apply the allowable moments and forces of the tanks or any equipment, we need to go and check the location of the local coordinates and what is exactly the local coordinates. For example, you'll find that this calculation is taken on the shell of the tank, not the top of the nozzle of the tank, and they consider this as an X, and the circumferential force as Z, and the longitudinal force as Y. So luckily we are using the same coordinates, but in some cases we are using different coordinates, so we need to take care of this and shifting the equipment coordinates based on the global coordinates of our model. I will explain this more when we go to the pumps and the tanks. We will face it one, or more or less we will face it one time. So now we have our FR here. Sorry. Our FR is 310 077, so 310 0077. We just will apply here to fill out the empty forces, but we don't need it here. Also, we don't need the torsional moment here, but we just to fill it up. It's here times 8. Okay. Let's make our check. I don't have a problem. Make sure our displacement here. Okay. 13. Here. We make check. You can ignore this, it's not a big deal. Make sure our load case is right, then make one analysis again. And here in the nozzle check, we can check it against the operation. We don't check against the design case. And it mentioned that we are processed since we are safe. This is how we are making the calculation for the API 630 for the large storage tank. I hope this explanation was clear, and if you have any question, please ask me, and please subscribe to my channel and put the notification bell to follow up my next video, since I'm working on this series for the equipments and a lot of people was asking me about it. Thank you.